Hi everyone. So today we're going to spend some time talking about the forces that hold molecules together in the solids and liquids phases. These are what we often call condensed phases. As a reminder, what you've known so far in chemistry is that there are three physical states for every substance. They could be solid, liquid, and gas. We talk about the gas phase quite a bit when we talk about gases. And there we imagine that all the particles are separated. They don't have intermolecular interactions with each other. In fact, that's one of the assumptions we use to derive the ideal gas equation. But in the solids and liquid states, we have interactions between one particle and the other. And those are what we call intermolecular interaction, and the force that exists there is called intermolecular forces. The strength of these intermolecular forces is affected by pressure and temperature. So as temperature increases, each particle gets more kinetic energy, and as a result, at some point, the kinetic energy overpowers the intermolecular force, and the molecules then are able to escape the attraction between the one molecule and another. This also happens when you decrease pressure. So as you have fewer and fewer particles, pressure decreases, then the strength of that intermolecular force becomes weaker and weaker, and compared to the pressure, the lack of pressure that's exerted. And at some point, the intermolecular force then is no longer able to hold the molecules together, and we get a gas phase. But what we want to talk about today is really when the forces make a difference. In other words, we want to talk about these forces when the substances are in those condensed states that I mentioned earlier, which is the solids and liquid states. Uh, in these states, the particles can have electrostatic interactions, which is the same interactions we've been talking about all this time in the class, with neighboring particles. These interactions are what we call intermolecular forces, and you'll see that I'll shorten this as IMF. And what the strength and the type of these intermolecular forces are what we're going to spend some time talking about, because those specifics about the intermolecular forces would then determine the melting point, boiling point, viscosity, and other physical properties of these substances. So generally speaking, you can sort of consider these forces to be in three different scenarios. They could be very weak forces between one particle and another. They could be medium strength forces, and they could be very strong forces. Because all of these are electrostatic in nature, these forces, there's always two factors that determine the strength of that interaction. One is the distance between the two electrostatic partners, the positive and negative charges. And the second is the size of each of these charges. So if you have a +2, for example, interacting with a -2, that would be a stronger interaction compared to a +1 interacting with -1 at the same distance. If you have a +1 and -1 at a closer distance, that would have a stronger interaction compared to plus and -1 at a longer distance. Just to remind you that we talked about this equation before, which is Coulomb's equation, and that's really what it's telling you, is that that electrostatic interaction depends on the combination of the charge effect as well as the distance between those charges. So from here on out, I would just talk a little bit about the different types of intermolecular forces that exist in solids and liquids that are keeping the solids and liquid structures together. So the first type of intermolecular force that exists in solids and liquids is something called a hydrogen bond. And a hydrogen bond is a type of force that exists if you have a covalent molecule that has a hydrogen bonded to another atom in it. And those atoms have to be electronegative enough. And so as a result, we usually only classify something as a hydrogen bond if the hydrogen is covalently bonded to nitrogen, oxygen, or fluorine. Okay? And again, what we're talking about here when we say hydrogen bond is not the bond between the hydrogen and these electronegative atoms. It's really the intermolecular attraction that occurs between that hydrogen and the neighboring electronegative atom. So let me explain a little bit. Because these electronegative atoms have higher electronegativity than hydrogen, they are going to attract the electrons in the covalent bond towards themselves. As a result, when we draw the distribution of electrons in this covalent bond, the electronegative atom will have more electrons, so we call it delta negative, and then the hydrogen would be slightly less electrons, so we would call it delta positive. In other words, this is positive relative to that atom. Because this is positive and this is negative, now you have a dipole, right? And so if another dipole with that hydrogen covalently bonded to another electronegative atom happens to be around, then they can make interactions. The negative side of that dipole can make interaction with the positive side of another dipole, and vice versa on this side. These green dots here is what we call hydrogen bond, okay? So again, I want to emphasize that it's not this covalent bond that's called the hydrogen bond. That's just a covalent bond. This here is what we call a hydrogen bond. So it's an intermolecular between molecules force. So here I'm illustrating a textbook example of a molecule that has hydrogen bond, which is water. You look at water, it has O and H covalent bonds. O is more electronegative than H, so you have your delta negative, delta positive centers. Here you have your dipole. And then if you have another water molecule coming over, you can form these hydrogen bonds between one water molecule and another water molecule. Okay? And again, I want to highlight that it's not this bond that we call the hydrogen bond, but it's this interactions right here. Okay? Now, we can also have a dipole when hydrogen is not present. As long as we have a more electronegative atom on one side and a less electronegative atom on the other side, bonded covalently, that would cause that charge distribution where one side is delta negative and the other side is delta positive. So here I'm illustrating that type of interaction that occurs when you have an XY covalent bond where X is more electronegative, so it's delta negative, and Y is less electronegative, so it's delta positive. If you have another XY molecule nearby, the X on one molecule and the Y on the other molecule can make interactions. These type of interactions we just generally call dipole-dipole interaction because it's interaction between two dipoles. In this particular case, the Y, the less electronegative element, is not hydrogen. It's usually a nonmetal like carbon, silicon, but it's not hydrogen. If it's hydrogen, then we would call this interaction hydrogen bond. Here are examples of groups that might generate dipole-dipole interaction anytime you have a CO bond, a CN bond, or a CF bond. The C here would be delta positive because all these O, F, and N are more electronegative than the C. And as a result, if you have a molecule that looks like this is acetone, where there's a CO bond, that C on one acetone molecule can interact with the O on the other acetone molecule, making that dipole-dipole interaction, which is highlighted in green. The last type of intermolecular interaction that would be important is when you have two nonpolar molecules. It turns out that even though nonpolar molecules are not really charged, in other words, they don't have these dipoles, actually there is a possibility that these nonpolar molecules could generate a temporary dipole, and I'll talk about that in a second. When those temporary dipoles are generated, then the interaction between one nonpolar molecule and another one is called a London dispersion force type of interaction. Okay? Now, let me talk a little bit about nonpolar molecules. As you understand it, nonpolar molecules have a uniform charge distribution. In other words, the positive and negative are uniformly distributed. There's no one side that's more positive. There's no one side that's more negative. But it turns out that there is a little bit of a difference in the polarity of a nonpolar molecule. One side might be just slightly less positive, and the other side might be just slightly more positive. As a result, because the molecule is slightly polarized like this, so one side is slightly more positive, the other side is slightly more negative, it's possible that once you have this molecule exist, that it would induce the neighboring molecule to also be polarized. So the picture looks something like this. You have two nonpolar molecules, like hydrogen gas in this case. due to temporary fluctuation in electron density, one side of the hydrogen molecule becomes slightly more negative, the other side becomes slightly more positive. If there's another neighboring hydrogen molecule next to this one, that positive on this end of the hydrogen molecule will induce this side to form a negative charge because it would repel positive and it would attract negative. As a result, that neighboring molecule now develops a negative charge on this side. If it develops a negative charge on this side, in other words, more of the electrons go to this end of the molecule, then you have less electron on that side, which means that side is going to be positively charged or more positively charged compared to this side. As a result, now you have two dipoles. They're very weak, as you can imagine, because they're made by these temporary connections, but these two dipoles can then interact with each other. That interaction is what we call the London dispersion force interaction. So I just want to highlight here on a slide to show you the different types of interactions or intermolecular forces or intermolecular interactions that could occur. We've highlighted only three of these, which is hydrogen bond, dipole-dipole, and London dispersion, because those three are the ones that we will see most commonly. However, if you have an ion and a dipole present, you can also have an ion-dipole interaction. That will be like an interaction between, for example, sodium ion and water molecule. Okay, so they're different species now, but they can have that interaction. The one that we've been talking about are all when you have the same species present. So hydrogen bond is between two water molecules, dipole-dipole in this case is between two ICl molecules, and London force is between two F2 molecules. But when you have two different molecules, you can have these other intermolecular forces present as well. One of the things I want to highlight is the strength of these intermolecular forces. They are all by far weaker than the type of bonding we've talked about in topic 8. So when we talk about ionic and covalent bonds, those are much stronger interactions. So an ionic bond roughly on average would be about 700 kilojoules or more stronger, right? So that's the energy needed to break an ionic bond. Covalent bond roughly runs around 400 kilojoules per mole of bond. You can see that the hydrogen bond is only worth about 10 to 40, so roughly about 30 kilojoules per mole, which is about 10 times weaker, okay, than the covalent bond. And then this dipole-dipole is even weaker than the hydrogen bond. And then the London forces is, of course, the worst. That one is only about, 1 to 2 kilojoules per mole of bond. So it's a lot. It's about 10 times weaker than a hydrogen bond.